Okay, so back to doing this guy. So first thing I did, draw my curve, put in my rectangles, and I have chosen equal width rectangles that met on the right side of each rectangle, right-hand endpoints. Then we're going to start doing the problem. Delta x. Delta x is always going to be b minus, if we're using equal width rectangles, which we are, b minus a over n. In this case, since we're on the interval from 0 to 3, zoom in just a little bit, see a little bit better. We're on the interval from 0 to 3, 3 minus 0 over n, 3 over n. Let's figure out what x sub k is. And so really doing the same thing we did last time. X sub 1 is my starting point plus the width of one rectangle. So in this case, 0 plus delta x, so 0 plus 3 over n. X sub 2 would be my starting point plus the width of two rectangles. That's to say width of two rectangles. Two rectangles. I'll have to fix that someday. So that's going to be 0 plus 2 delta x, or in this case, 2 times 3 over n. X sub 3, starting point, times 3 times the width of, I'm just leaving out the word of, width of one rectangle. That would be better. Width of. Don't you love watching me make corrections to the notes while you're watching these videos? Width of one rectangle. Width of one rectangle. And so that would be 0 plus 3 delta x, or 0 plus 3 times n, and so on. And then in general, my starting point, x sub k, is going to be the starting point plus k times the width of what rectangle, or that is start plus k delta x. That is how you're always going to find x sub k. It's your starting point plus k delta x. So in this case, 0 plus k delta x, or in this case, k times 3 over n, or that's going to be 3k over n. But there is your basic thing here. That x sub k is going to be your start plus k delta x. That's what you need to remember as far as the x sub k. This was me just trying to build up why x sub k was that. So, the integral from 0 to 3 of 2x squared plus 1 dx is going to be the limit as n goes to infinity of k equal 1 to n f of x sub k delta x. That really is just the formula for the area of a rectangle. This is height times width. It is just the formula of the rectangle. There is no way that looks like the word width. Let's try again. Width. That looks like width. That all that x sub k delta x is really just the area of a rectangle, height times width. That delta x represents the width, the f of x sub k represents the height. So in this particular problem, and it's going to be as n goes to infinity of k equal 1 to n of f, and then we calculated that x sub k was 3k over n, and delta x was 3 over n. I got a bad break right there. That should be up there. So we'll get rid of that. Fix that later on, bad break there. So replace x sub k with what it was equal to. Xk was equal to 3 over n, 3k over n. Delta x was equal to 3 over n. And now we are just going to start all that algebra again. Next note, the summation variable is k. So the 3 over n is a constant in the summation, so 3 over n can be factored out of the summation. So all I did there was take that 3 over n, factor out of the summation, but it's still in the limit. It can come out of the summation because the variable for the summation is k. And so this is just a multiplied constant. It can come out of the summation. Next, we're going to apply the function 2x squared plus 1. So all we did was apply the function 2x squared plus 1. So 2, square all that stuff, plus 1, and we start to simplify. So 3k, quantity squared would be 9k squared times 2, 18k squared over n squared plus 1, to simplify. Then I'm breaking up the summation, because the limit of a summation is the sum of the limits. That was the wrong phrase. The summation of a sum is the sum of the summations. That's what I meant to say. That you can break up summations by addition. That's all we did there. Then if we look at this guy right here, again, important to remember, the variable of the summation is k. The variable of the summation is k. So I'm looking just at this guy right here. That means the 18 and the n squared they're just multiplied constants. And so they can factor out of that first summation. And so that's what I've done here. I've just factored out that 18 over n squared. So I have the limit as n goes to infinity of 3 over n times the quantity 18 over n squared times the summation from k equal 1 to n of k squared, and then plus the summation from k equal 1 to n. And the reason why we broke it up and did that factoring, I have formulas for those. Apply formulas of that k squared equals n times the quantity n plus 1 times the quantity 2n plus 1 all over 6, and k equal 1 to n is c times n. So applying my formula, so basically I take that entire summation of k squared and I replace it with its entire formula. The formula for the summation of k squared is n plus 1, 2n plus 1 over 6. Replace k squared with its formula. Then I've got the summation from k equal 1 to n, replace it with its formula, very explicitly, 1 times n. And now we just start to simplify. So what did I do first? And there is more than one way to simplify through it here. What I did first here was note that the 6 and the 18 cancel, leaving 3. And the n squared cancel, leaving n. So I have 3n plus 1, 2n plus 1 over n, and then 1 times n is n. Then I distributed the 3 over n. So if I distribute the 3 over n, the 3 times the 3 is going to give me 9. The n times the n is going to give me n squared. So 3 times 3 gives me 9. N times n gives me n squared. So that's what I have for the first term. Second term distributing, the n's are going to cancel, leaving me just 3. So all we did in there was distribute the 3 over n. Foiled there. Distributed the 9. Then split that limit up into 2 limits, because I know how to do each one of these. Here, the limit of a rational function, the degrees are equal, so I can just pull off those coefficients, specifically 18 over 1 for 18. The limit of a constant is the constant, so 3, 18 plus 3, 21. And so we have found that the integral from 0 to 3 of 2x squared plus 1 dx equals 21. And because this region was above the x-axis, this also is the area. The area under this region from 0 to 3, you don't see the 3 there, but there should be a 3 right there. 0 to 3, that area is 21. And we integrated that by the limit of a Riemann sum. Now, your calculator will actually do these. Now, I've got an old calculator here, so here's what an old calculator looks like. Let me quit all that. Math. If you arrow all the way down to FNINT and hit enter. Old calculator here. So let's start over so you couldn't see it all. Clear. If you hit your math key, arrow down to FNINT, which stands for function integrate. And this is an old calculator. On TI-84s, they actually give you the template for the definite integral. So for the older, and then you just fill in the pieces. For the older integral, first thing you put in is the integrand, which was 2x squared plus 1. Then comma, where's the comma? Comma, the limits of integration was 0, comma, 3, and then comma, x, which represents the dx. So the integrand, 2x squared plus 1, the limits of integration, 0 and 3, and then x, which represents the dx. On a newer calculator, it actually gives you a little template, and you just fill in each one of those values. Then you hit enter, and I clearly didn't know the syntax. Okay, let's see if we can figure out what they wanted. Maybe they wanted the x there first. Let's try putting the x there. X, comma, 0, comma, 3. Let's try it that way. So I may have just gotten the order wrong. Enter, and it did it 21. So there's the order for the older calculators. Function, dx, which you're going to represent by x, then the limits of integration, 0 and 3. And it does it. Now, you are welcome to use your calculator for checking purposes. You're never allowed to use your calculator for finding the answer. If all you ever show me on a test is just the answer, you will get 0 points for that answer. So you can use it to check. Now, the calculator is working differently than we will be working. And so if the answer is going to come out, if the answer comes out pretty like this, you are going to get the same answer. But say trigonometry is involved and you come up with an answer of square root of 3 over 2. Your calculator is not going to give you square root of 3 over 2. It's going to give you a decimal approximation. So while the calculator is useful for checking, it's not going to be sufficient for finding answers. You will not get credit for finding answers. So if you've got an older calculator, there's the syntax. On a newer calculator, it actually gives you a little template that you can just fill in. But there we did a problem as a limit of a Riemann sum. What we're going to focus on mostly in this section, because there's going to be a much easier way to do definite integrals than what we have here, so we're not going to focus much anymore on this. We're going to focus on some properties of definite integrals. So properties of definite integrals. First, a happy little theorem. A continuous function is integral. That is, if a function f of x is continuous over an interval a to b, then its definite integral over a to b exists. So continuous functions you can always find, or somebody, or at least in theory, you can always find the definite integral. If it's not continuous, that's a different story, and we will talk about that in Calculus 2. Rules. The integral from a to b of f of x dx equals negative the integral from b to a of f of x dx. That is, interchanging the limits negates the integral. Because what you're doing, if we take this little picture here, a to b, we're measuring our intervals kind of in a positive direction. If we go b to a, you're measuring your intervals in a negative direction, and so those widths would become negative, which then switches the sign of the integral. So all you need to remember is that, really what you need to remember is that interchanging the limits negates the integral. The integral from a to a of f of x dx equals 0. If the upper and lower limits are equal, the integral equals 1, which makes perfect sense if we think about that in terms of area for just a moment. That would be saying, what is the area underneath the curve from a to a? Well, you didn't go anywhere, so you could not have created any area. So if the upper and lower limits are equal, the integral is 0, as long as the function is defined at that number, as long as we're defined at a. And we will end this video and pick up with the rules on the next video.